Hi. If you're watching this video, hopefully you're looking to get a little bit of Regents review while the New York State Chemistry Regents still exists the way that it does. Just a quick introduction, some best practices before we get started. The number one most important thing you can have available is right here. It's a QR code that's going to point you to the New York State chemistry reference tables. It has all of the information that you will get when you take the test, and arguably a lot of the information you're going to need to take the test. Things otherwise you might want to have, some sort of a calculator handy. And if you need a paper copy or digital copy of the Regents, there will be a link below. It is suggested that you take a look at these questions before you watch this video. It might move a little bit fast for some people, but hopefully you find this helpful, and let's get started. In case you're just joining us here, quick breakdown. Part A, this is the second half of Part A. This is 16 to 30 on the question numbers. Total of 30 multiple choice questions for the section for the whole year. We are looking more concepts rather than application and calculation. You're going to be seeing a lot of definitions, and depending on your teacher, this was in chronological order that you learned it. For this first question, entropy, it's a definition. So we've got a couple of different deltas that we can look at depending on what you've learned. This one is your entropy. It's a measure of disorder of the system, of randomness. It's really a measure of free energy, but let's not get too much into the definitions there. It's not accuracy, it's not precision. This would be percent error, and this would be standard deviation. Attraction of the nucleus for an electron, that's based on charge. I don't know quite how that fits with all this. General definitions of how the universe works. In general, we're going to be going towards lower energy and greater randomness. So that's going to be choice 3. If you need some letters and numbers to put near that, we're going to be using our delta G equation. In general, the universe functions in such a way that delta G is negative for a spontaneous process. We're going to talk about in nature as a spontaneous process. So we want this to be negative, so this needs to be less than 0, and this needs to be greater than 0 so that you're subtracting a positive from a negative to keep it below 0. For question 18, we're just going to go straight to the reference tables. Organic prefixes, they're cluing you in right here to go look at that. Table P is your organic prefixes. We're just going to match them up right here. Choice 1 is our answer. Hept is 7. Nice, quick, and easy. It does feel like there's a lot of these questions, just reading the reference tables is helpful. For 19, though, not so much. There are a host of organic reactions that you will see. You don't get them from the reference tables, you get them from experience. We could look at all the individual ones, but I'd rather not spend that time here. Some things that I can pop out really quick is that I see that there are some phase changes here. So we've got sublimation and deposition are showing up. These are phase changes. From the solid phase to the gas phase, that's sublimation. And from the gas phase to the solid phase is deposition. So these are not examples of organic reactions. They're in fact examples of phase changes, physical properties. So we're just going to knock out any of the answer choices that have any of them, and that leaves us with choice 4. Saponification is the reaction that creates soap from a fatty acid and a base, or a fat and a base, creating fatty acids, which are fatty acid anions, which are soaps. And fermentation is the process where a carbohydrate is worked on by an enzyme in yeast to make alcohol and carbon dioxide. For question 20, we are able to use the reference tables a little bit more extensively. They give us the functional groups, so I'm going to go straight to the table that labels functional groups. Here we have our headings, so we're looking at this second column here. And all we got to do is find the one that matches up. I did highlight all 4 of the possible answers. We see this one is shown up in the first one here. The fact that this is just a bond to nothing is shown over on your general formula. That is the rest of the molecule. It can be a carbon or a group of carbons or even just a hydrogen in some cases. But regardless, this is a functional group that describes an aldehyde, not any of the other 3. Ooh, redox reactions. Okay, so there we're getting an idea for the order of things. Redox reactions, which particles get transferred? So there are 2 big acronyms that students use to kind of remember what's going on in a oxidation reduction or redox reaction. The first is Leo and Gur. Leo the lion says Gur. And the second one's oil rig. I'm going to use the first one because this E here, lose electrons, is oxidation, and gain electrons is reduction. That's what they stand for. And in both cases, we're highlighting the E to say that the thing that gets transferred, gained, and lost is electrons. Half reactions represent half of a redox reaction, so we're still looking at redox reactions. And redox is two words put together. That's reduction and oxidation. And like we saw in the last slide, lose electrons is oxidation, gain electrons is reduction, or oil rig. Oxidation is losing, reduction is gaining, but regardless of the ones listed here, we have oxidation as a half reaction. Distillation is a separation method. Sublimation we already talked about, and vaporization, like sublimation, is a phase transition from liquid to gas. Voltaic cell, electrical energy. So if we're talking about voltaic and electric energy, the voltaic cells, you're converting chemistry into electricity. And for the electrolytic cells, you're converting electricity into chemistry. Both of these fall under the term electrochemical cells, which is just anything that's converting chemistry and electricity. The idea being that a voltaic cell is like a battery, where a chemical reaction gives you flowing electrons, and electrolytic cells the opposite, where you push and pull electrons to cause a chemical reaction to take place. But regardless, if we're converting to electrical, that's this one here. We're going from chemical to electrical, breaking and making bonds, causing electrons to flow, generating power somewhere else. For acids and bases, tables K and L are going to be your best friends. Which one is an Arrhenius base? Arrhenius bases create OH minus aqueous ions as the only anion in solution. So if you don't remember that, though, you can just look at your common bases, and usually for the Regents, we're going to pick whichever one shows up on the table. So our answer here is going to be 3. Now, I know what you might be thinking. If you remember your definition and you don't look it up, I see an OH there. Not every OH in a compound becomes a hydroxide ion when that compound is dissolved in water. CH3COOH is found down here, and this is, in fact, an acid. We saw in Table R that there were some of these COOH functional groups a few questions ago, and yeah, that chemically in solution behaves very differently to a base, so our answer here is 3. In a neutralization reaction, well, a neutralization reaction is going to be when an acid and a base react. So if you don't remember this one off the top of your head, it is possible to somehow reason out an answer. If we copy over an example acid and example base, which I'm just going to copy over, the first ones from the tables, acids and bases undergo double replacement reactions. This is 2 compounds in solution. That means the cation switch, or the lead atoms, I guess, switch. The Na and the H are going to switch, which will give us NaCl and HOH, which can be then rewritten as H2O. So really what we have here is salt and water, ionic compound in water, so that's going to point us over here. So this isn't really an organic reaction, but similar to the organic reactions, this is one that you can put in your head, or in this case, you can figure it out. One acid-base theory. So we did just talk about one acid-base theory from the Arrhenius definition. Bases will create hydroxide in solution. So here as an example, we've got sodium hydroxide dissolving into water, making sodium plus and hydroxide minus. If you went down the list for sodium hydroxide, potassium hydroxide, and calcium hydroxide, you'd see that pattern over and over again. But ammonia, this aqueous ammonia, does not have any O's in its molecule. So I don't know how you're ever going to create a hydroxide ion if you don't have O's. The alternate acid base, another acid base theory, it's known as the Bronsted-Lowry acid base theory, instead looks at how bases work through chemical reaction. We're going to react our ammonia with water. Your clue here is that it says aqueous, right? Like that's that hint, like, hey, there's water here. This one's in equilibrium, and here it's going to act as the base because we're going to make an ammonium ion and then a hydroxide ion. So here, our base, our hydroxide, comes about through water reacting with your ammonia, creating this ammonium cation. So here, you have to try and think about what the ammonia does to become the NH4. You can see that this lost an H+, so this would gain an H+. And the one that fits best there is H+ acceptor for the base. There's your answer. We don't want H2. These are hydrogen. These are not ions. These are molecules. All right, we're wrapping things up. We're on to nuclear chemistry. Based on Table N, I've copied the relevant information here. We're looking at uranium-238 and 235. That's these two here. They have different. We're looking for what's different. Well, I can see that they have the same decay mode, so I'm turning that out. Number of protons, well, that's not shown, but since they're both uranium, and all elements are defined by their number of protons, they both have 92 protons in their nucleus, and since they are atoms, usually, unless you hear different, they also have 92 electrons, so we're really only left with 2, but just to confirm, they do in fact have different half-lives, about 4.5 billion years and 700 million years, so yeah, different enough. 28. The charge in the nucleus of an atom that converts the atom from a change. Ooh, I read the word wrong. A change that converts an atom from one element to another. So if we wanted to go back really quick, and let's take this U-238 for an example. An example reaction here would be a change that creates something else. We know this decays through alpha decay we just saw. So if we're doing some conservation of particles, we'd be left with 90 on the bottom for a total of 92 and 234 on the top. Now the fact that this is 90 means that it can't be U because U has 92 protons in its nucleus. Number 90 would be thorium. So the idea here is we're converting one element to another element. This is an example of what we call a transmutation, changing from one thing to another. Substitutions are organic reactions. Single replacement is not really put into a category, but it's certainly not changing one element into another. We're replacing one element with another in a compound, but we're not changing the nucleus. And oxidation reduction, as we saw, has to do with electrons, not the nucleus. So our answer here is 4. Which radioactive emission has the greatest penetrating power and the least ionizing power? The different types of radiation that we've seen can be blocked with different things. This is why you wear a lead vest if you go to the dentist and get x-rays, because we're trying to block that radiation. Again, I'm leaning on compound chemistry. Thanks. I'll put a link below if you want to look at this larger. But right here we've got ionizing ability and how penetrating. So how penetrating is shown here, where the particles are making it through different layers of shielding. Here we have paper and aluminum and lead, and the same with the other ones. Alpha particles can be stopped by paper. Beta makes it through paper, stopped by some sheet of metal, and then gamma makes it mostly stopped by a sheet of lead. So we want the greatest penetrating power. Already I'm kind of leaning towards gamma as a possible answer. Positron's not even on the list. We're not going to worry about it. And the least ionizing power. So we have that information in our top row here. Ionizing ability or ionizing power is the ability of your radiation to pull electrons away from other matter. Since gamma radiation has no mass and no charge, it's just light, high energy light, it is not going to ionize much of anything. It does a little bit. Your alpha particles being that big positive helium nucleus, that's going to be ionizing much better. Which statement describes a benefit of using fission reactions? So this one I'm going to use a little bit of English to answer. Benefit. Radioactive waste must be stored for a long time. That's not a benefit. That sounds like a drawback. Nuclear fuel consists of stable isotopes. I mean, it has some, but like those aren't the active parts. Gamma radiation is produced. Not a benefit. We're not trying to gain superpowers here. The big answer here is that large amounts of energy are produced per mole of reactant. I believe it is on the order of magnitude of thousands to even millions of times more energy, because breaking and making new nuclei is just way more energy than gaining and losing and transferring electrons. Hope you found this helpful. Thanks for watching.